There's a moment, and maybe you felt it before, looking up at a clear night sky far from any city, where something shifts. Not just intellectually, something deeper. Your chest gets a little tight, the ground feels less solid. Because in that one instant, the abstract numbers you've heard your whole life stop being numbers and start being real. Let's make that moment happen right now. The sun is so large that roughly 1 million Earths could fit inside it. That already sounds impossible. But the sun is considered a fairly average star. There are stars so enormous that if you placed one at the center of our solar system, its surface would extend past Jupiter. Not to Jupiter. Past it, you, sitting where you are right now, would be deep inside that star. In our galaxy, the Milky Way contains somewhere between 200 and 400 billion stars, each one potentially surrounded by worlds. That's just our galaxy. There are estimated to be 2 trillion galaxies in the observable universe. 2 trillion. And the observable universe is only the part we can see, limited by the speed of light and the age of time itself. What lies beyond that horizon isn't empty, it simply hasn't reached us yet. Now hold all of that in your mind, and then consider this. Every empire that ever rose and fell, every war ever fought, every love story, every funeral, every sunset anyone ever called beautiful. It all happened on a pale blue dot so small that from the outer edge of our own solar system, Earth vanishes completely into the background noise of scattered light. You are made of atoms forged in the cores of dying stars. The iron in your blood was born in a supernova explosion. You are ancient beyond your own comprehension, and at the same time, almost comically brief. Your entire civilization, agriculture, writing, cities, the internet, represents less than a single second in the cosmic calendar of this universe's existence. This isn't meant to make you feel worthless. Strangely, many people feel the opposite when they sit with it long enough, a kind of wild, aching wonder, because the universe didn't have to produce anything capable of looking back at itself and asking questions. And yet, here you are, doing exactly that. But here's where the vertigo gets a second layer. Because as humbling as that scale is, there's something even more unsettling waiting just beneath the surface. And it has nothing to do with how big the universe is. It has to do with how much of it we actually understand. There's a strange comfort we reach for when the universe starts to feel too large. We retreat into facts, into what's been measured, confirmed, mapped. We say, at least we know this much. And for a moment, that feels like solid ground. But let's actually look at that ground. Everything we've ever observed, every galaxy cataloged, every star named, every particle tracked inside an accelerator, accounts for roughly 5% of what the universe contains. 5. The rest is something else entirely. Dark matter, which we cannot see but infer from the way gravity behaves in places where there's nothing visible to cause it. And dark energy, even stranger, which appears to be driving the universe apart at an accelerating rate, a force so pervasive it outweighs everything we've ever directly detected, and yet we have almost no idea what it actually is. So when scientists say we understand the universe, what they really mean is, we understand a thin, luminous slice of it, the part that glows. And even within that slice, the mysteries stack up fast. We know the speed of light, we don't know why it's that speed and not another. We know quantum mechanics works. It's the most precisely tested theory in the history of science. But we cannot fully reconcile it with general relativity, the theory that governs everything at large scales. 2 frameworks, both correct, both irreconcilable. The deeper structure that should unite them remains, for now, out of reach. We have mapped the cosmic microwave background, the faint afterglow of the early universe, and it tells us extraordinary things about where we came from. But it also raises questions we can't answer. Why is the universe so uniform across regions that, according to our own models, could never have been in contact with each other? Why does it have the specific constants it has, the precise strength of gravity, the exact mass of the electron, when even a slight variation in any of them would mean no stars, no atoms, no anything? These aren't gaps at the edges of knowledge, they're holes at the center of it. And then there's consciousness, the fact that the universe somehow arranged itself into forms that can ask questions about the universe. We don't know why awareness exists. We don't know if it's rare or everywhere. We don't even have a working definition of what life fundamentally is, beyond a loose cluster of behaviors we've agreed to call living. The honest picture then is this: we are a species that has done something genuinely remarkable. We've looked up, built instruments, written equations, and pulled back the curtain on a staggering amount of structure and order. That's not nothing, that's extraordinary. But the curtain, it turns out, opens onto another curtain. And behind that, another. Which brings us somewhere uncomfortable and thrilling at the same time. Because if what we can observe leaves this many questions, imagine what lies in the territory we haven't touched yet. Imagine the questions we don't even know how to ask. And one of the deepest, oldest, most disorienting of those questions isn't about what the universe is. It's about where it came from. Not just the stars, not just the first atoms, but the moment before any of that. The moment, if there even was a moment, before time itself began. There's a question that stops most physicists cold when they hear it asked out loud. Not because it's complicated, though it is, but because it exposes something almost embarrassing about our most celebrated theory of existence. The question is simple: what happened before the Big Bang? The standard answer, for decades, has been that the question itself is meaningless. Time, as we understand it, began at the Big Bang. Asking what came before is like asking what's south of the South Pole. The grammar seems to work, but it points at nothing. There is no before. That answer has always felt a little too convenient, and increasingly, physicists aren't satisfied with it either. Here's what we do know, roughly 13. 8 billion years ago, everything we can observe, every galaxy, every atom, every photon of light that has ever traveled through this universe, emerged from a state of almost incomprehensible density and heat. Not an explosion into empty space. Space itself expanded. The universe didn't grow inside something. It was the something. And it has been stretching, cooling, and complexifying ever since. From a featureless plasma into stars, into planets, into you sitting wherever you are right now, wondering about all of it. That story is extraordinarily well supported. The cosmic microwave background radiation, faint light left over from 380,000 years after the Bang, maps that early universe with stunning precision. We can read it like a baby photo of reality. The ratios of hydrogen and helium in the cosmos match exactly what the theory predicts. The large-scale structure of galaxies, the way they cluster and filament across billions of light years, traces back cleanly to quantum fluctuations in those first fractions of a second. The math works, the evidence holds. And yet, push the equations far enough backward toward that original moment and physics doesn't break gracefully. It breaks catastrophically. Density becomes infinite. Temperature becomes infinite. The equations produce what mathematicians call a singularity, which is a technical way of saying the universe hands you a number that means nothing, a divide by zero at the heart of creation. Most physicists treat this as a signal, a flare in the math telling us that our current tools simply aren't adequate to describe what actually happened there. It's not that a singularity existed, it's that our theory stops being able to see. So what might actually have been happening? One serious proposal, not fringe speculation, but genuine theoretical physics, is eternal inflation. The idea goes like this: our Big Bang wasn't a beginning so much as a transition. Before it, there was a vast, perhaps infinite quantum field in a state of furious exponential expansion. In most regions, this expansion never stops. It just keeps going, forever, faster than light can cross it. But in rare pockets, the field loses energy and drops into a lower state. And that drop, that phase transition, releases an enormous burst of energy. A Big Bang. A universe. Our universe would be one such pocket, one bubble in a sea of eternal, frothing inflation. And if that's true, other bubbles have formed, are forming, will form. each one a universe unto itself, with its own physics, its own constants, its own possible versions of complexity and life. A multiverse, not as metaphor, but as physical consequence. Others take a different route entirely. Loop quantum cosmology suggests that space and time are not infinitely divisible, that at a small enough scale, they become granular, like pixels. And if that's true, the singularity disappears. You can run the equations backward through the bang and find not a beginning but a bounce. A previous universe that contracted, reached a minimum volume, and then rebounded outward into expansion. Our universe emerging from the collapse of another. An endless cycle of death and renewal written into the geometry of space-time itself. Then there is the stranger possibility that Stephen Hawking explored with James Hartle, the idea that time near the Big Bang behaved more like a spatial dimension. That asking what came before is genuinely like asking what's north of the North Pole. Not because the question is forbidden, but because the topology of space-time simply curves away from it. No edge, no wall. Just a smooth, closed geometry with no moment you could point to and call first. Each of these ideas is honest about what it doesn't know. None of them is proven. What they share is something more important than certainty. They're all serious attempts to stare past the edge of what our physics can see and ask whether the edge itself is real or just the limit of the flashlight we brought. What's extraordinary is that these aren't just philosophical musings, they make predictions. The pattern of fluctuations in the cosmic microwave background might carry faint imprints of a pre-Big Bang era. Future telescopes, listening to gravitational waves from the earliest moments of the universe, might eventually let us hear echoes of whatever came before. We built ourselves out of stardust and learned to ask where the stars came from. Now we're reaching for whatever made the conditions that allowed the stars to exist at all. But here's the thing about origins. The deeper you dig, the more you realize you're not just excavating the past. You're uncovering structure, invisible architecture that shapes everything you can see. And most of that architecture, it turns out, is made of something we cannot touch, cannot photograph, and still don't fully understand. Something that outweighs all the ordinary matter in the cosmos by a factor of 5, that bends the light of distant galaxies and holds entire clusters of stars together. And that remains, even now, almost entirely unknown. You can't see it. You can't touch it. No instrument ever built has detected it directly. And yet, right now, it is holding entire galaxies together, including the one you live in. After everything we explored about the birth of the universe, the violent expansion, the first light, the gradual coalescence of matter, you might assume that the stuff we can see, the stars, the planets, the gas clouds, the billions of glowing galaxies, you might assume that's the universe. That's the main event. But it isn't, not even close. Everything you have ever seen, everything science has ever measured, every atom that has ever formed a mountain or a human being or a supernova, all of that visible matter makes up roughly 5% of what the universe actually contains. 5%. The rest is dark. Literally, structurally, stubbornly dark. Let's slow down here because this is worth sitting with. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies. Hundreds of them bound together by gravity, moving together through space. He calculated how much mass those galaxies would need in order to hold themselves in formation. Then he calculated how much mass he could actually see. The numbers didn't match, not slightly. They were off by a factor so large it bordered on absurd. Something invisible was providing enormous gravitational force. He called it Dunkel Materia, dark matter. Most of his colleagues ignored him for decades. Then, in the 1970s, an astronomer named Vera Rubin started mapping how galaxies rotate. Here is what physics predicted. Stars on the outer edges of a galaxy should orbit slower than stars near the center, the same way Pluto moves more slowly around the Sun than Mercury does. Gravity weakens with distance. That's the rule. But Rubin's data showed something completely different. The outer stars were moving just as fast as the inner ones, sometimes faster. The rotation curves were flat when they should have been falling. The only explanation that held up was that each galaxy was embedded in a vast, invisible halo of mass. Mass that emits no light. Mass that interacts with nothing except gravity. Rubin's data was careful, meticulous, repeated across dozens of galaxies. It was impossible to dismiss. Dark matter wasn't a rounding error. It was the dominant structure of the cosmos. Think about what that means architecturally. The galaxies you see in photographs, those luminous spirals, those sweeping arms of stars, they are not the structure. They are tracings on the surface of something much larger and much darker. Dark matter forms an enormous cosmic web, a skeleton of invisible filaments stretching across billions of light years. Ordinary matter, gas, dust, stars, falls into the gravitational valleys carved by this skeleton and pools there, lighting up. The galaxies are, in a sense, ornaments on a framework we cannot see. Without this invisible architecture, galaxies would fly apart, clusters would dissolve. The large-scale structure of the universe, those vast filaments and voids you see in deep field images, would never have formed. Dark matter didn't just show up after the universe was built. It built it. It provided the gravitational seeds around which everything else collapsed and condensed in the early universe, turning a uniform fog of particles into the structured, intricate cosmos we inhabit. And we still don't know what it is. The leading candidates are particles, hypothetical ones, given names like WIMPs or axions or sterile neutrinos. Experiments buried deep underground, shielded from all interference, have been waiting for decades for a single dark matter particle to bump into an ordinary atom and leave a trace. Nothing definitive has arrived. Particle accelerators have searched for signatures of it in high-energy collisions. Still nothing. It does not emit light, does not absorb it, does not interact with electromagnetism in any way we've been able to measure. It is, in the most literal sense, beyond our current reach. Some physicists have proposed alternatives, modified theories of gravity that might explain the observations without invoking invisible matter at all. These theories work for some observations, but they struggle badly with others, particularly the behavior of colliding galaxy clusters, where dark matter and ordinary matter appear to separate under the forces of impact, leaving a clear gravitational fingerprint in places where no visible mass exists. The evidence keeps pointing back to the same conclusion. There is something there. It is vast. It is real. It shapes everything, and it refuses to introduce itself. Here is what makes this genuinely strange to contemplate. You are moving through dark matter right now. This room, this planet, this entire solar system is passing through a diffuse halo of it as the galaxy rotates. Billions of these particles, if they are particles, may be streaming through your body every second, interacting with nothing, leaving no trace, invisible to every cell and every instrument you possess. The universe we see is not the universe that exists. It is the luminous 5%, floating inside something vast and dark and gravitationally dominant that we have not yet learned to read. But dark matter, for all its mystery, is at least holding things together. What comes next is different, stranger in a way that strikes at the very fate of everything. Because while dark matter pulls inward, something else is pushing outward, something embedded not in matter but in space itself. And it is winning. If dark matter is the skeleton of the cosmos, the hidden frame holding everything together, then dark energy is something far stranger. It doesn't pull, it pushes, and it's winning. Here's what took scientists decades to accept. The universe is not just expanding, it's expanding faster than it was yesterday, faster than it was a billion years ago. The galaxies aren't simply drifting apart the way debris scatters after an explosion. They're accelerating away from each other, as if space itself is being stretched by something with no name and no known source. That something is what we call dark energy. We didn't go looking for it, it found us. In 1998, two independent teams of astronomers were studying supernovae. the brilliant deaths of massive stars, using them as cosmic measuring sticks. The math they expected was simple. Gravity slows things down over time, so the expansion of the universe should be decelerating. What they found instead stopped them cold. The distant supernovae were dimmer than they should have been. Not slightly. Systematically. The only explanation that made sense was one nobody wanted. The expansion wasn't slowing. It was speeding up. The discovery won a Nobel Prize. It also broke cosmology open like an egg. Because here's the uncomfortable truth. We don't know what dark energy is. We have a name for it. We have measurements of its effects. We know it makes up roughly 68% of everything that exists in this universe. But its nature, its origin, what it actually is at a fundamental level? Blank, a mathematical placeholder wearing the costume of an explanation. One leading idea reaches back to Einstein, who once inserted a term into his equations of general relativity called the cosmological constant, a kind of built-in repulsive force he added to keep the universe static, and then later called his greatest blunder when Hubble proved the universe was expanding. Now that constant has returned from the grave, resurrected not as a blunder, but as a candidate for the most consequential force in existence. In this interpretation, dark energy isn't a thing moving through space. It's a property of space itself, energy that the vacuum carries simply by existing, constant and everywhere, humming quietly in every cubic centimeter of emptiness. That emptiness, it turns out, may not be empty at all. Another possibility is something called quintessence, a dynamic field, not a constant, something that shifts and evolves as the universe ages. If quintessence is real, dark energy might have been weaker in the past and could grow stronger in the future. Or weaker. We genuinely don't know which way it bends. And that uncertainty isn't a gap waiting to be filled by the next paper. It's a fundamental wall at the edge of our current physics. What we can say is this: dark energy is slowly, inexorably winning its war against gravity. Every second, the space between galaxy clusters stretches a little more. The most distant galaxies we can see today will eventually cross a threshold, a cosmic horizon, beyond which the universe expands so fast that even light from them can no longer reach us. They will vanish, not destroyed, simply unreachable forever. The observable universe is already smaller than the actual universe, and it's shrinking in scope with every moment that passes. If this continues, and there's no confirmed reason to think it won't, the universe's long-term future looks less like a fiery collapse and more like a slow, cold dissolution. Stars will burn out. Galaxies will drift beyond contact. Eventually, the cosmos will become an almost featureless void, a darkness so complete that any civilization unlucky enough to exist at that point would look out into the sky and see nearly nothing, with no way of knowing what had come before. But that's billions upon billions of years away. And before we reach the silence at the end of time, there are places in the universe where the laws themselves already seem to have surrendered, where space and time compress into something no equation fully survives. We've talked about the invisible scaffold of matter. We felt the push of an energy with no face. Now we go somewhere that doesn't just challenge understanding, it ends it. We've just finished talking about dark energy, a force that stretches space itself, quietly accelerating the destruction of everything. But if dark energy represents the universe dying at its edges, then black holes represent something even stranger. They are places where the universe simply stops making sense. Let's be honest about what a black hole actually is, because the word gets thrown around so casually that we've almost forgotten how deeply wrong it is. It's not a hole. It's not empty. It's the opposite of empty. It's a region where matter has been compressed so completely, so violently, that gravity wins against everything, against light, against distance, against the very laws that make physics possible. At the center sits the singularity, and here's where language starts to fail us. A singularity is a point of infinite density, infinite, not very high density, not density beyond what we can measure. infinite. That word, in mathematics, is often a polite way of saying, our equations gave up. When your best theory of the universe produces the answer infinity, what it's really telling you is that something fundamental broke. General relativity, Einstein's masterpiece, one of the most tested and confirmed theories in all of science, collapses inside a black hole. It produces nonsense. Useful, beautiful nonsense, but nonsense nonetheless. And then there's the event horizon. This is the boundary, the threshold, the point of no return. Cross it and nothing, not matter, not light, not information, ever escapes. From the outside, watching someone fall into a black hole is one of the most surreal experiences physics allows us to imagine. You'd never actually see them cross the horizon. Time dilation stretches their fall eternally from your perspective. They slow, they redden, they fade, but they never quite arrive. To the person falling, however, they cross it in a moment. They might not even notice, and then, perhaps in seconds, they're gone. This is what happens when time itself becomes a direction. Inside the event horizon, moving toward the singularity isn't a choice. It's as inevitable as moving forward in time is for you right now. You cannot stop it. You cannot choose otherwise. You are falling, and forward is the only direction left. Stephen Hawking spent decades studying black holes and eventually discovered something that shook everyone who thought they understood them. Black holes evaporate. Slowly, imperceptibly, but they radiate energy, what we now call Hawking radiation. And over unimaginably long timescales, they shrink and eventually vanish. Which raises a question so devastating, it has occupied the greatest minds in physics for 50 years. What happens to all the information that fell in? The structure, the history, the patterns of every particle that ever crossed that horizon. Does it disappear? Because if it does, that violates a principle so fundamental to physics that losing it would mean reality itself doesn't work the way we think it does. We call this the black hole information paradox, and it remains unsolved. Think about what we're really saying here. We have found places in the universe where our theory of the large general relativity and our theory of the small quantum mechanics are forced to coexist, and they refuse to. They produce contradictions, they produce infinities, they produce paradoxes, and we don't know how to reconcile them. Black holes are not just exotic objects in a distant galaxy. They are the universe's way of pointing at the crack in our deepest understanding and saying, you haven't figured it out yet. There are supermassive black holes at the center of almost every large galaxy, including ours. The one at the heart of the Milky Way is called Sagittarius A star, and it weighs 4 million times more than the Sun. In 2019, we photographed one for the first time, a blurry orange ring around darkness, 55 million light-years away, and still it made people cry. Because seeing the unseeable feels like something sacred. But here's what stays with you. The boundary of a black hole, that event horizon, is not just a physical threshold. It's an epistemological one. It marks the edge of what any observer outside can ever know. There is an entire region of the universe that is, by definition, forever hidden from us. Whatever happens inside, whatever physics operates inside, we cannot observe it, cannot test it, cannot confirm it. It exists outside the reach of science as we currently practice it, which raises a question that might seem absurd, but isn't. If there are regions of the universe sealed off from observation, if physics breaks down at singularities, if our best theories contradict each other at the extremes, then how many other realities might exist that are simply outside our reach? Not hidden by distance, not hidden by darkness, but hidden by the fundamental structure of what reality allows us to see. That question, strange as it sounds, is exactly where we're going next. We've just stood at the edge of a black hole, a place where the laws of physics collapse into silence. But what if the universe itself doesn't stop there? What if, beyond that silence, there isn't nothing, but everything? This is where the multiverse comes in. and it will make the black hole feel almost comfortable by comparison. The idea begins simply enough. Quantum mechanics, the science of the impossibly small, tells us that particles don't have fixed states until they're observed. Before you look, an electron isn't here or there, it's both. It exists in what physicists call a superposition, a blur of all possible conditions at once. The moment you observe it, it collapses into one reality. One answer, one outcome. But a physicist named Hugh Everett looked at that moment of collapse and asked a question that changed everything. What if it doesn't collapse? What if instead of choosing one outcome, the universe splits? And both outcomes happen, each in its own separate branch of reality. That's the many worlds interpretation. And it's not a metaphor. Everett meant it literally. Under this framework, every quantum event, every particle interaction, every probabilistic flicker at the subatomic level generates a branching. The universe doesn't decide, it duplicates. And since quantum events are happening constantly, everywhere, in every atom of every star and stone and living cell, the branching never stops. The number of parallel universes isn't large. It's incomprehensibly, functionally infinite. Now here's where it stops being abstract and starts being personal. If the branching is real, then there is a version of this moment where you made a different choice this morning. A version where a different job, a different city, a different life unfolded from a single fork in the road you didn't even notice. There's a version of you who never heard this, and a version who heard it and walked away, and a version who heard it and it changed something. All of them equally real, none of them able to reach the others. The multiverse doesn't only come from quantum mechanics though. Cosmology offers its own version, and it's even harder to hold in your mind. During the first fractions of a second after the Big Bang, the universe expanded at an extraordinary rate, a process called inflation. Most models of inflation suggest it didn't stop uniformly. Different regions stopped inflating at different times, each cooling into its own bubble, its own universe, with potentially different physical laws, different constants, different rules for what matter and energy can even do. In some of those bubbles, atoms may not form. In others, gravity might pull too hard for stars to survive. In a vanishingly rare few, conditions land exactly right for complexity, for chemistry, for life. We happen to live in one of those. Whether that's luck or selection or something else entirely, no one can say. What makes the multiverse so difficult and so fascinating is that we can't test it directly. By definition, other universes don't send us signals. They don't appear on any instrument. The evidence is mathematical, indirect, and deeply contested. Some physicists consider it the most elegant explanation for why our universe's constants are so precisely tuned. Others consider it an untestable ghost story dressed in equations. And yet it refuses to go away. Because the alternative, that this one universe with these exact laws simply happened to be the only one that exists and happened to be perfectly suited for us, feels like an explanation that raises more questions than it answers. So we are left holding something strange, a theory that might be true, that might explain everything. That would mean you are not singular, that you are, in some sense, countless, living every version somewhere, never meeting, never knowing. It's a thought that expands the mind almost to breaking. But here's the thing about the universe. Once you start looking at the scale of what exists, one mystery doesn't end cleanly. It opens into another. We've asked whether the universe is one or infinite. Now comes a quieter question, and in many ways, a darker one. If the universe is this vast, this old, this full of potential, why haven't we heard a single word from anyone else in it? Why, across all that infinite silence, is there nothing but us? We just finished imagining infinite versions of you scattered across parallel universes. Now flip the question entirely. If the cosmos is that vast, that generous with space and time and possibility, where is everyone else? This is the Fermi paradox, and once it gets under your skin, it stays there. The numbers are almost offensive in their implications. Our galaxy alone contains somewhere between 200 and 400 billion stars. A significant fraction of those stars host planets. A significant fraction of those planets sit in the so-called habitable zone. Not too hot, not too cold, the right conditions for liquid water, for chemistry, for life. Even if you apply the most conservative estimates, even if you assume life is rare and intelligence is rarer, the math still produces millions of civilizations that should exist, or should have existed, somewhere out there in the Milky Way. And that's just our galaxy. There are roughly 2 trillion galaxies in the observable universe. So where are they? That's exactly what physicist Enrico Fermi asked over lunch in 1950, almost casually, and nobody at the table had a good answer. Nobody still does. Here's what makes the silence so unsettling. The universe is about 13.8 billion years old. Earth is only 4.5 billion years old. That means there were civilizations that could have formed, evolved, and spread across the galaxy, billions of years before the first cell ever divided on this planet. Even at speeds far below the speed of light, even with slow, methodical expansion, a civilization with enough time could colonize the entire Milky Way within a few million years. A few million years sounds enormous. On cosmic timescales, it's a Tuesday afternoon. And yet, silence. No signals, no megastructures, no visitors, no traces. Scientists call this the Great Filter. The idea is that somewhere along the path from dead chemistry to a civilization capable of crossing the stars, there's a wall. Something that almost nothing gets past. The terrifying question isn't whether the filter exists. The terrifying question is whether we've already passed it, or whether it's still ahead of us. If the filter is behind us, that's almost good news. Maybe life itself is extraordinarily rare. Maybe the leap from simple cells to complex organisms happened once or twice in the entire observable universe by sheer improbable luck. In that case, we're the miracle. We're the exception. The silence makes sense because there's almost nobody else to make noise. But if the filter is ahead of us, if civilizations routinely get to roughly where we are and then collapse, destroy themselves, or hit some ceiling they cannot break through, the silence becomes a warning. Some researchers have proposed softer explanations. The universe is big, and signals travel at the speed of light. Maybe everyone is out there, but the distances are simply too enormous. The messages still on their way, arriving in a million years. Maybe civilizations choose silence intentionally, broadcasting nothing because broadcasting is dangerous. Maybe we're looking in the wrong way, listening for radio waves when advanced intelligences moved on to forms of communication we haven't even conceived of yet. Maybe we're in a cosmic wildlife preserve, and someone decided it's better not to interfere. Every solution to the Fermi paradox is somehow unsatisfying. Every answer opens a new wound in the logic. The one that keeps astronomers awake isn't the dramatic ones. Not the dark forest theory, not the simulation theory, not ancient civilizations turning themselves into black holes. The one that keeps them awake is simpler. We have been searching in earnest for only a few decades. The observable universe is 93 billion light-years across. We are a species that just figured out fire 200,000 years ago. Our silence detectors are young. Our reach is almost nothing. Maybe the universe isn't answering because we don't yet know how to listen. Or maybe, and here's the thought you should sit with, the silence itself is information. The universe's blankness isn't absence, it's a clue. Something shapes the destiny of civilizations. Something powerful enough to leave an entire galaxy quiet. And we are inside that story right now, somewhere in the middle of it, unable to see the ending. Which brings us somewhere unexpected. Because the moment you start asking why the universe is silent, you start pulling on a thread that leads directly to something even stranger than alien life. It leads to the nature of time itself, and the possibility that time, as you experience it, is one of the universe's most elaborate illusions. We've been staring into the silence of the cosmos, asking where everyone is. But here's something that might reframe that question entirely. And honestly, it might reframe everything. What if the reason we can't find them, the reason we can't quite grasp the scale of what's out there, has something to do with a mistake we've been making since the moment we were born? A mistake so fundamental, we built our entire civilization on top of it. We think we understand time. We don't. Time feels obvious. It moves forward. The past is gone. The future hasn't arrived. And you are here in this present moment, reading these words. That's just reality. Except physics, when you push it hard enough, tells a completely different story. And the deeper you go, the stranger it gets. Not strange in a quirky, fun way. Strange in a way that makes you question whether the word now means anything at all. Let's start with something Einstein showed us over a century ago. Something we've confirmed thousands of times since, and something that still doesn't quite fit inside a human brain. Time is not a constant. It bends, it stretches, it slows down depending on where you are and how fast you're moving. An atomic clock on a satellite ticks faster than one on the ground. Not metaphorically, measurably, precisely faster. GPS systems would fail within minutes if we didn't correct for this effect. Time dilation isn't a theory we're waiting to prove. It's an engineering reality we depend on every day. But that's the gentle version. Push further and you get to something physicists call the block universe, or eternalism. In this view, time isn't something that flows. Past, present, and future all exist simultaneously, like pages in a book. The book doesn't change as you read it. You move through it. The moment of your birth and the moment of your death are both already there, fixed coordinates in a four-dimensional structure. Nothing is becoming. Everything simply is. This isn't fringe thinking. It follows directly from special relativity. When two observers move at different velocities, they disagree about what's happening right now, somewhere else in the universe. Your present moment and my present moment can be genuinely different, not because one of us is wrong, but because simultaneity isn't a universal fact. It's a local one, which means the present isn't a slice cutting through reality. It's a perspective, and if different observers have different nows, then no single now is more real than any other. They all exist. Sit with that for a second. The moment your grandparents met, the last conversation you regret. A Tuesday afternoon 3 years from now. These aren't places that have disappeared or haven't arrived yet. In the block universe, they're all there. Static, permanent. The sensation of time passing, of things changing, of one moment giving way to the next. That's something happening in your mind, not in the fabric of space-time itself. And then there's the question of entropy. Because here's the puzzle. If the laws of physics work equally well forwards and backwards in time, and most of them do, then why does time feel like it only moves in one direction? Why do we remember yesterday and not tomorrow? Why does an egg break but never unbreak? The answer points toward entropy, toward the tendency of systems to move from order toward disorder. But entropy only explains the arrow, the direction. It doesn't explain why time moves at all. The equation works both ways. The universe, mathematically, has no preference, which means the flow of time might be an illusion. A very convincing one, built by minds that evolved to predict the future and remember the past. We are creatures of sequence, so we experience sequence. But sequence might be something we project onto reality, rather than something reality actually contains. Now here's where it gets personal. If time is a structure rather than a river, if it doesn't flow but simply exists, then what are we? We're not travelers moving through time. We're patterns embedded in it. Threads woven into a fabric that doesn't go anywhere, because it's already everything, everywhere, all at once. The self you think of as continuous, as journeying from past to future, might be more like a line drawn across a map. The line doesn't move, it's just there. Some physicists have gone further still, suggesting time might not be fundamental at all, that it might emerge from something deeper. the way heat emerges from the movement of particles. That at the smallest scales, at the quantum level, time may simply dissolve into something our language doesn't have words for yet. Loop quantum gravity hints at a universe where time only appears once you zoom out far enough. Zoom in too close, and it vanishes. We carved our entire experience of existence around time. Our memories, our hopes, our grief, our anticipation, all of it is structured by the assumption that time is real and that it moves. And yet, the most rigorous descriptions of reality we've ever constructed quietly suggest that this might be the grandest illusion of all. Which leaves one last unsettling thought. If time as we experience it isn't real, if reality is a fixed structure and our sense of moving through it is something our consciousness constructs, then what is consciousness exactly? What is the thing doing the experiencing? What is the thing reading these words right now, convinced it exists in a present moment that physics says might not be a universal truth? That question doesn't just brush against philosophy. It walks directly into the possibility that what we call reality, the whole thing, not just time but space, matter, you, me, all of it, might not be what we assume it is. In fact, there are serious scientists and thinkers who have started to wonder whether it could be something else entirely, something constructed, something running, and that is exactly where we need to go next. We've just pulled apart the fabric of time, shown how it bends, stretches, slows down, how your past and my present might be occupying the same moment depending on where we're standing in space. And if that already made reality feel unstable beneath your feet, then what comes next might dissolve the ground entirely. Because there's a possibility, taken seriously by physicists, philosophers, and some of the sharpest minds in technology, that none of what you're experiencing right now is physically real. Not the chair you're sitting in, not the light coming through your window, not even the atoms that make up your hands. What if this universe, all of it, is information? A simulation running inside something we cannot see, cannot reach, and may never understand? This is not science fiction. It's called the simulation hypothesis, and its logic is uncomfortably difficult to dismiss. Here's where it starts. Think about the history of computing. In just a few decades, we went from machines the size of rooms that could barely calculate arithmetic, to devices in our pockets that can render entire three-dimensional worlds in real time. Worlds with physics, with weather, with characters that respond and adapt. Now project that forward. Not 10 years, not 100, thousands, millions. If a civilization survives long enough and keeps advancing technologically, at some point it will have the ability to simulate conscious minds inside artificial environments, so detailed, so layered, so responsive, that the beings inside would have no way of knowing they weren't real. And here's the part that stops people cold. If even one civilization ever reaches that point, just one, anywhere, anywhen, they wouldn't run just one simulation. They'd run thousands, millions. The number of simulated realities would vastly outnumber the one base reality, which means statistically, when you ask the question, am I in the real universe or a simulated one, the honest answer is, the odds are not in favor of real. This is philosopher Nick Bostrom's trilemma, and it forces a choice between three possibilities. Either virtually all civilizations go extinct before reaching the technology to simulate realities, or virtually all advanced civilizations choose not to run such simulations, or we are almost certainly living inside one right now. There's no comfortable fourth option. You have to land somewhere in that triangle. Now, some people hear this and immediately reach for dismissal. It sounds like a conspiracy theory dressed in mathematics. But look at what physics itself has been quietly uncovering. The universe, at its deepest level, appears to be made of information. Not matter, not energy, information. John Wheeler, one of the great physicists of the 20th century, spent his later years arguing for a principle he called it from bit. The idea that every particle, every field, every physical thing derives its existence from binary choices, from answers to yes or no questions. The universe, he believed, is fundamentally computational. And then there's the pixelation problem. Quantum mechanics tells us that reality, at the smallest scales, is not continuous. Space itself may have a minimum length, the Planck length, below which nothing can be divided further. Things don't exist in smooth gradients at the quantum level. They exist in discrete steps, in quantized packets. If you were designing a simulation and needed to conserve processing power, rendering reality in discrete units rather than infinite resolution is exactly what you do. It's how every video game in history has worked. The question is whether that's a coincidence. There's something else. The laws of physics are unreasonably elegant, unreasonably consistent. They follow mathematical rules so clean, so symmetrical, that physicists have long found it strange, beautiful but strange. Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. Why should the physical world obey math at all? Why should equations written on a whiteboard describe galaxies and also atoms, and also the bending of light? Unless the universe isn't just described by mathematics, unless it is mathematics, unless it's code. And yet, none of this proves anything. That's the razor's edge of the simulation hypothesis. It explains a great deal, and it proves nothing. There may be no experiment you could ever run from inside a simulation to confirm you're inside one. Every tool you use to test reality is itself part of the reality you're testing. It's a closed loop. A snake swallowing its own tail. What changes if it's true? Some people find the idea terrifying. The self dissolves, meaning collapses. Nothing matters if it's just computation. But consider the other direction. The pain you felt was real enough to shape you. The people you love, simulated or not, have changed who you are. If consciousness can arise in code, then the experience of being alive is no less genuine for having a different substrate than we assumed. The question of what's real may matter less than the question of what's experienced. And if someone is running this simulation, if there is an architect somewhere beyond the edge of what we can observe, then one strange thought follows naturally. They built a universe with 8 billion years of history, 100 billion galaxies, the quiet impossibility of consciousness asking questions about itself. Whatever their reason, they didn't build something small. Which brings us to a question that might be even larger than who built it. What happens to it in the end? Because whether this universe is physical or computational, it is not static. It is moving towards something. And what waits at the finish line of existence, every possible ending, every scenario science has seriously entertained, is where we're going next. There's a question that has haunted astronomers, philosophers, and anyone who has ever stared at the sky long enough to feel small. Not how the universe began. We've been circling that. But how it ends. And here's what makes this different from everything we've discussed so far. The simulation hypothesis was a question about what's real. This is a question about what's final. Because even if reality is exactly what it appears to be, even if we're not in a simulation, even if consciousness is exactly what we think it is, the universe still has an expiration date, maybe several possible ones. And scientists have mapped them all. Let's start with the one that sounds most familiar, because familiarity is deceptive here. The universe is expanding. You probably knew that. But what you might not fully feel yet is that it's expanding at an accelerating rate. Something, we call it dark energy, which is really just a name for our confusion, is pushing galaxies apart faster and faster. And if that acceleration continues without limit, you arrive at the first possible ending, the Big Rip. Picture it. Over trillions of years, galaxies drift beyond each other's sight. Then, closer to the end, the expansion becomes so violent that it starts tearing things apart at smaller and smaller scales. Galaxy clusters shred apart, then individual galaxies, then solar systems, then planets, then, in the final moments, and we're talking moments in the cosmic sense, billions of years compressed into a frantic finale, atoms themselves are ripped apart. The very fabric of matter loses its coherence. Space expands faster than anything can hold together. The last sound, if sound could exist, would be silence before it even had a chance to form. But maybe dark energy doesn't accelerate forever. Maybe it plateaus. Maybe it fades. If it fades, or if it's simply not strong enough to overcome gravity at the grandest scales, the expansion slows, stops, reverses, and you get the big crunch, which is the universe collapsing back into itself. Every galaxy falling toward every other galaxy. Temperature rising, density rising, time running backwards in a sense, not literally but structurally. Everything that the Big Bang unfolded, folding back up. The universe returning to a singularity, to a point of infinite heat and density. Some theorists believe this might not be an ending at all, but a bounce. A new Big Bang emerging from the collapse. A cycle without beginning or end, universe after universe like waves on an ocean no one can see from shore. Then there's the stranger one, the quiet one, the big freeze. Sometimes called heat death, doesn't require any drama. No ripping, no crunch, just entropy winning. The second law of thermodynamics is patient. It doesn't rush. It simply states that systems move from order to disorder, and it has infinite time to be right. Stars burn out. Black holes slowly evaporate through a process called Hawking radiation, releasing energy in whispers across eons until they too are gone. Eventually, across a time frame so vast that the current age of the universe looks like the first millisecond of a human life, everything reaches the same temperature. No gradients, no heat flowing anywhere, no work being done, no information changing hands. The universe doesn't die violently, it just stops happening. It becomes a state rather than a process. Existence without event. There's something philosophically unbearable about that one, isn't there? Not because it's painful, but because it's indifferent. And then, this one is newer, stranger, and somehow the most unsettling of all. There's the false vacuum. Quantum field theory suggests that the universe might be sitting in what physicists call a metastable state. Like a ball resting in a small dip on a hill. Not at the lowest point, just stable enough to stay put. For now. If the quantum fields that underpin all of reality are in this false vacuum, then at any moment, anywhere in space, a bubble of true vacuum could nucleate, a point where physics snaps to its actual lowest energy state. That bubble expands at the speed of light. Not faster, exactly the speed of light, which means you would never see it coming. No warning, no signal, no last thought. The bubble wall rewrites the laws of physics as it passes. Atoms, forces, constants, everything restructured or simply incompatible with existence as we know it. A universe-ending event that is, by definition, impossible to observe from inside. 4 endings. One of them might already be in motion. And yet, and this is what I want you to hold, none of these endings are moral failures. None of them mean anything was wasted. The light from a star that burned out a billion years before the Earth existed still traveled, still arrived, still mattered to whatever was here to receive it. Which brings us somewhere unexpected. Because after everything, the quantum strangeness, the dark matter we can't see, the consciousness we can't explain, the simulation we can't rule out, and now these endings we can't escape, you might expect the conclusion to be despair. It isn't. What all of this adds up to, when you let it settle rather than fight it, is something that looks much more like freedom than terror. And that's exactly where we're going next. There's a moment that happens to almost everyone who stares too long at the night sky. A quiet vertigo. The stars stop being beautiful and start being threatening. The distances become real, and suddenly you feel it. How small you are, how brief your life is, how indifferent the cosmos seems to the fact that you exist at all. It's a natural reaction. But I want to suggest that it's also, in a very specific way, wrong. Not wrong because the universe is actually friendly. It isn't, particularly. Not wrong because you matter in some cosmic ledger somewhere. You don't, not in the way we usually mean. Wrong because the feeling assumes that size determines significance, and that's a confusion we've inherited, not a truth we've discovered. Think about what you just learned. The universe may end in a slow fade, heat death, 1 trillion years from now, the last stars cooling into silence. Or it may tear apart, or collapse, or bounce into another cycle entirely. These are real possibilities that physicists hold with genuine seriousness. And here's the strange thing. None of those endings change what happens at the scale where life actually occurs. The physics of a heartbeat are not diminished because the universe will eventually run out of usable energy. The moment you understand something for the first time is not made hollow by the existence of a big rip 100 billion years away. The ancient Stoics had a practice they called memento mori, a reminder of death. Not to induce despair, but to do the opposite. When you know something ends, you pay attention. You stop assuming you have infinite time to start caring. The universe's fate works exactly like this, just at a scale so vast it bends the mind. Knowing the stars will go out makes this particular night, with this particular sky still burning above you, feel like something you should not waste being afraid. There's also something genuinely stunning hiding in all of this. You are not separate from what you've been watching. You are the universe comprehending itself. The hydrogen that fused in stellar cores billions of years ago is sitting inside your body right now. The same laws that govern black holes govern the neurons firing as you listen to these words. You didn't arrive into this universe. You emerged from it. And that means the mystery you've been staring at outward is, in some very real sense, the same mystery you carry inside you every single day. The questions that remain open, dark matter, dark energy, the origin of everything, the fate of everything, these aren't signs that science has failed. They're signs that the universe is deep enough to keep surprising us. Every answer so far has opened into a larger question. That's not frustrating. That's the most honest description of wonder that exists. So here's what I want to leave you with. The universe is under no obligation to be comprehensible. The fact that it is, even partially, even provisionally, is not obvious. It didn't have to be this way. Patterns didn't have to hold. Mathematics didn't have to describe reality. The cosmos could have been noise all the way down. Instead, we get structure. We get elegance. We get laws that a mind can actually follow if that mind is willing to go far enough. You have that mind. You just used it to travel from the Big Bang to the possible ends of time, through black holes and colliding galaxies, and the quantum foam beneath everything. That's not nothing. That's extraordinary. And the vertigo you might feel at the edge of all this, that's not a warning to look away. It's the feeling of being genuinely alive inside something genuinely immense. Don't waste it on fear. If this journey meant something to you, if one idea landed differently, if one image stays with you, subscribe to this channel because there are more of these waiting for you. Hit the like button. It does more than you think to help this reach someone who needs it. And leave a comment. Tell me which part shifted something. Tell me what question it opened up for you. I read them. And honestly, your questions are where the best videos come from. The universe isn't finished with us yet.